Welcome back to Cougar Chem Tutoring. I'm Austin, and I'll be running through part 2 of problem set 10, naming and bonding. Number 4, name these polyatomic ions. Poly, meaning many, okay, many, and atomic is atoms, okay, atoms. So these are ions that are made of many atoms, meaning multiple atoms. So previously we've been working with monatomic ions, so just one atom ions, which like Na plus or Cl minus, right? They're just made of one atom with a charge, okay? In this case, we got multiple elements, and then this compound itself has a charge. So these are just, this concept, the polyatomic ions, is one of the few concepts in Chem 105 that they just make you memorize directly, okay? These are just, you just have to know these. Unlike the equation sheet, which is given to you on a test, or the electromagnetic spectrum, or conversions like pounds to kilograms, or even constants like Planck's constant, right? These are actually things that you would have to bring to the test memorized, okay? Unlike those other things. So what I'd like to do is kind of use kind of a pattern that we see throughout these naming. You're welcome to take a screenshot of this. I'm not able to upload this to YouTube in the description section in any way. You're welcome to screenshot this sheet. This was made by a student that I had back in my section a while ago, named Miriam Wilkes Freeman. She's awesome, brilliant student, made this chart to kind of help us memorize the polyatomic ions in a way that was simpler than just straight memorization, okay? So the key here is knowing what the base ion is, okay? The base ion is going to be your key factor. Base ions always end in 8, okay? And you'll notice that the first element that we had here has PO4, okay? O4 is not always in the 8 section. It's usually in the per 8 section, but there are two exceptions with sulfate, okay, and phosphate, okay? So what you have to do is take the first part of the name. So this was phosphorus, right? You take the first syllable and take off the second syllable and add 8. So this would be phosphate, okay? Or this would be, here we've got a sulfur, okay? This would be sulfur. We're just going to take off the second syllable here, and we're just going to add 8, okay? So this would be sulfate, okay? And this would be phosphate. So we've actually just answered the first, one of the first 3 here. So we got phosphate and sulfate. Now, it's not listed here, but technically, if they were to ask you, what does phosphite look like? You would say, okay, I know that phosphite, the phytes, anything that ends in "ite" always has one less oxygen than the base ion, okay? So you could accurately say this is probably PO3, and it will always follow the same charge as the base ion, okay? So it's going to be 3 minus, okay? So you could technically tell, just by, if they had given you the name, by knowing the base ion, that you could get to other ions, okay? So we've got another base ion in part B. We've got a carbon, and you can probably guess that this one's going to be carbonate, and this one's one of the ones that breaks the rules as far as the first syllable. You actually use both syllables in this case. We don't call it carbate. We just call it carbonate, okay? So that's another base ion that you'd have to know. Sulfate and phosphate, both base ions that you'd have to know. All right, so now we're getting into funky ions. So this has an extra H plus attached to it, so it looks like sulfate, which it partially is. But when we have another hydrogen attached to it, we actually call it bi. We put a bi in front of it. And it just represents that it's only partially neutralized, okay? It was a 2 minus, now it's partially neutralized into just a 1 minus. And so we say bi, and this would be just sulfate, which is what you see here, right? Bisulfate. Okay, so all we did here was add an H plus to SO4 2 minus, so it neutralized one of the negative charges, and it became HSO4 minus, which we call bisulfate, okay? All right, so this one is just another one that you just have to straight memorize. Now, we're in the O4 region again, but now we're with a halogen. So that's where the biggest difference comes in, is when you have an O4 and a halogen. The halogens, remember, if you look on the periodic table, the halogens are in this last group over here. They're in the 7th group, so fluorine, chlorine, bromine, and iodine. Really, we don't use chlorine for these oxo anions. We just use chlorine, bromine, and iodine, okay? If those are attached to an O4, that's when you're going to use the other rule, the other naming, okay? So if we look down here, that is where we get these guys right here. Whoops, right here, okay? So this is perchlorate, okay? So we have that chlorine, right? It was chlorate because of the O3 minus. Then when we added another oxygen, it became perchlorate, okay? So the per is just like saying there's a 4th one here, okay? So this is perchlorate. Now, knowing that pattern, if I told you if I asked you what was this, BrO4 minus, you could tell me, oh, that's okay. I know it would be bromate if it was O3 minus, but I know that using the pattern here, that since there's a 4th one, I'm going to call it perbromate. Okay, so by knowing just, kind of the basics here, you can kind of figure out a bunch of other ones. All right, so now we're going on to letter F. So we got HCO3 minus. Okay, so up here we had CO3 2 minus, and notice that when we added the H here, we called this bisulfate, right? And it was sulfate. It went from sulfate to now bisulfate. Same thing here. We're going to call this now bicarbonate. You've probably heard of maybe sodium bicarbonate. That's just baking soda, right? Sodium bicarbonate is literally just Na, which was a plus, right? But now it became a compound with HCO3. That's bicarbonate. Okay, that's sodium bicarbonate. All right, so letter G here, we've got, this is just another base ion. So base ions will typically be O3 minuses with the exceptions of sulfate and phosphate, okay? So now I've got a base ion. I'm going to look at what that is. Okay, I've got NO3 minus. It should be an 8, right? And what can you guess? If this is nitrogen, right? This was nitrogen. Nite was the first syllable. So I'm going to say nitrate. Okay, nitrate. So that's what it is, nitrate. All right, now we've got this guy. So now I've got a halogen attached to an oxygen with a charge. So I'm going to look at that. Remember, this one follows kind of a funky rule. So now I'm at the base ion, which would have been ClO3 minus. Okay, but now I've taken off 2 oxygens. So 1, 2. And when we take off one, we turned it into ite, right? Like sulfide or phosphite, like the example we gave here. But when you take off a second oxygen and you're left now with 1, you actually add another suffix to it, kind of like what we did with the 4, but now we're saying there's only hypo means a deficient in. And so we would say hypo, and then this would be hypochlorite instead, okay? So this would be hypochlorite. So I'm still using the prefix, or the one syllable from chlorine, chlorite. It was chlorate, went to chlorite by going down 1, and then it went down 2. We call it hypoite. Hypochlorite in this case. All right, and this one's pretty easy. This one's just the mercury ion, so we just call it mercury. Okay, there's not much more you need to know about that one. Just remember that there's 2 of them attached to each other, not 1. All right, so now we've got this one. Now, if this one was nitrate, right, we're down 1 oxygen. Okay, so since we're down 1 oxygen, I'm going to go down 1 by calling this nitrite, right? Nitrite is 1 less oxygen than nitrate. All right, last one. This one is one that does not follow the same patterns that you just have to memorize. This is called acetate, okay, acetate. And you'll see it written differently. Sometimes you'll see it written as like COO, H3COO minus as well. It just depends on, or let me think, H3C. C2OO or something like that. Okay, it's kind of funky sometimes how they write it, but just remember there's 2 carbons, 3 hydrogens, and 2 oxygens, and then it's a -1 charge. Okay, so this is acetate. And just to clarify, to make sure that we got all the ions here, I just want to kind of show you the other ones that we could have possibly in some of the problems that you might see later. So we've got bisulfate, which we covered, but we also have hydrogen phosphate. You may hear it called biphosphate. It's not as common because there is a possibility of having 2 hydrogens attached to it. So saying hydrogen versus dihydrogen is really important. But then we have bicarbonate, like we covered earlier. Hydroxide. Hydroxide is the ion that comes from water. Okay, water splits up into H plus and OH minus, and then when they come together, they become H2O. So we call it hydroxide. And then we have the cyanide ion. It's just a Cn minus. And then we cover the acetate one. And there are some rules here that you may want to review on your own. I'm not going to review them in this part of the video, but you're welcome to screenshot this as well and just kind of check to make sure that you know them. And then lastly, there's only 2 cation ions that you would need to know for this class. One is called ammonium. Okay, ammonia. Okay, ammonia is NH3, and then when you add an H plus to it, it becomes ammonium. So this is ammonia, NH4 plus. This is ammonium. Okay, ammonium. All right, and then you got hydronium, which is another water ion, but what it is a water molecule, and all we did was add an H plus to it. Okay, and it became the H3O plus hydronium ion. You'll use this ion a lot more in Chem 106 than you will in 105, but it's good to know for this class as well. All right, so on to number 5 then. Write the chemical formula for the following compounds. Okay, these chemical formulas, because we've been covering ions, will be ionic bonds. Okay, so based on what we've done in the previous video on naming, we'll kind of use those rules now with these polyatomic ions to see if we can name them as well. right, so the letter A here, we've got potassium chlorate. Okay, so potassium, where's potassium? Potassium's right there. Okay, so I know that potassium is K plus, okay, because it's in the first group. And then chlorate. What was chlorate? Chlorate was, okay, I know that begins with Cl. And remember, the most base ions will be O3, right? And all the halo-oxo anions, meaning the ones with halogens like chlorine, bromine, and iodine, will always be 1 minus charged, okay? So all you have to do is, remember, switch these up, the superscripts, and then you get the following. K, ClO3, and that would be the answer, okay? All right, now iron 3, now we're mixing in now a metal cation with Roman numerals with a few other concepts. So let's write iron 3. We know that when Roman numeral 3 is shown, that we have a 3+ charge on our cation, okay? And then we've got sulfate. What was sulfate? That's a base ion, and it's one of the 2 base ions that has 4 oxygens, okay? And then you will need to know, just need to memorize that it's a 2 minus charge, okay? What can help is knowing that sulfur usually has a 2 minus charge. It will take on a 2 minus when it makes this polyatomic ion. Same with phosphorus. When phosphorus makes an ion, right, it's usually a P3 minus. When it makes these ions with oxygen, it also creates a 3 minus charge, okay? So hopefully that that could help you a little bit. So, and then this tetrahydrate throws a lot of people off because we don't really cover it a ton. But all it means is that we've added 4. So tetra would be 4. And then hydrate just means waters. So 4H2O. And you just kind of draw this like funky little like multiplication symbol dot thing in the middle just to signify that. You don't have to know a ton about that yet. So just leave it at that, okay? Tetra would mean 4. Hopefully you know some prefixes like penta. Penta would be 5. Hexa would be 6. Hepta would be 7. There's not a ton of it. I honestly don't remember any of those on the test. So I wouldn't freak out too much about it. I know a lot of students do at first, but just worry about the first part here. The first part is definitely something that they can test you on really well. So let's go. We're going to switch the superscripts, right? Now I've got Fe, now it's 2, right? And then what you have to do is put parentheses now, because now we're talking about the entire molecule itself. This is SO4, 3, because there are 3 sulfate molecules that would have to neutralize the 2 3+ charges coming from the two iron atoms. Okay, and this is what this would look like, except now we're adding the 4H2O to make sure we get rid of and take care of the tetrahydrate there. So this is what your answer would be. We can't reduce these down, right? And so that it just becomes that's the most common denominator, and so that's what we have to do. Okay, so 2 and 3. All right, so sodium sulfide. So now we've got sodium. Where's sodium? Sodium's right there, and that means it's got a 1+ charge, right? Now sulfite. Okay, this is not sulfide. This right here is sulfide, right? We talked about maybe potassium sulfide, right? Where we switched them. This would be K2S. This is potassium sulfide with a D. Okay, this is sulfite with a T. They're 2 different things. So remember, sulfite is one of those polyatomic ions where it's deficient 1 oxygen than the base ion. Okay, and so this is going to be SO3. And remember, sulfur is going to be the 2 minus charge. So we got Na, and then we're going to switch the superscripts. We got Na2, SO3. And you don't have to put parentheses here because it's assuming that we just have 1 of each of those. So this would be our answer here. All right, D, we got sodium bicarbonate. Okay, sodium again, Na+. Bicarbonate, what was that? We actually had it up here, right? Bicarbonate just means there's a hydrogen attached to it, and we've got the carbonate ion neutralized by 1 charge. And so we've got HCO3 minus, and that just becomes NaHCO3. Okay? All right, lead 4 acetate. Where is lead on the periodic table? It's kind of weird. Just remember peanut butter. Peanut butter, think of peanut butter as like heavy or something. That's how I remember lead. I don't know why, but PB is lead. Okay, so lead, and what Roman numeral is this? That is a 4+. That's 4, okay? So lead 4, acetate. What was acetate again? Remember, it's one of those ones that doesn't follow the pattern, so you'll have to go down here. Here's acetate, so CH3CO. All right? So I'm going to put CH3COO minus, okay? So that's one way that you could see this. Now switch the superscripts, and you get PB, and then parentheses CH3COO, and then 4, right? So that's why we have to put the parentheses around that, because we're covering the whole polyatomic ion right there. All right, sulfuric acid. Now this is where it gets different. So we haven't seen acids yet. When we're talking about an acid, ic will come from the prefix ate, okay? So that means sulfuric came from sulfate, okay? Sulfuric came from sulfate. Okay, so the way that I like to do this is say ate to ic, or ite to is, O-U-S, okay? So adic and itis, okay? Adic and itis, that's, I don't know why I remembered it like that. It seems like it's a poem, but it's not. It just say adic and itis, and that should get you, hopefully make it easier when you're naming acids. This is particularly only for acids, okay? I'll just put acids. All right, so sulfuric acid. So I know that sulfuric came from sulfate, so I'm going to write SO4, 2 minus. Okay, now what is an acid? An acid is defined by having H plus that can dissociate away from it. So what that means is you have to have enough hydrogens to neutralize that charge. Hydrogen comes in H plus, okay? And if you have a 2 minus charge, that means you need 2 1 plus hydrogens to neutralize that. So that's what this is what this would look like. It would be H2SO4, because I'd be combining this with this, and I have to put the cation ion first, right? So H2SO4, that is sulfuric acid, okay? If they had said sulfurous acid, so sulfurous acid, okay, sulfurous, you're like, okay, us, adic and itis. So us came from ite. Okay, so sulfite. What does sulfite look like? SO3 and then 2 minus, and then I'd have to use hydrogens to neutralize that. So there'd be H2SO3, just like that. Okay, so those are the patterns of naming for acids. We don't get too in depth with them, other than just naming. We don't, like, as far as the chemistry goes behind acids, we don't really cover them in this class. You just have to know how to name them. All right, last one, sodium cyanide. Sodium, we said, was Na+. Cyanide is one of those ones that doesn't follow the pattern, so we got to look here. Cyanide, okay, cyanide, Cn minus. Okay, so I'm going to say NaCN. Okay, that would be sodium cyanide, because when I switch these superscripts, right, it's just going to be 1 to 1. So it's going to be NaCN. So that would be sodium cyanide. All right, and then number 6, they're asking us to do the exact opposite. So now they're saying, what are the names of the following compounds? And here it is extremely important that you know the charges on each of these, because if you don't know the charges, you're going to mess up the answer. And I'll show you how you can do that. For example, if you don't know the charge for carbonate, let's say you thought carbonate was a 1 minus, okay? That would mean if these came together in a 1-to-1 ratio, this would be copper. This would be a 1 plus, right? So we would call this copper, and then we'd put Roman numeral 1, and then carbonate, right? But that would be wrong, because carbonate is actually a 2 minus, right? 2 minus, and in order for these to come together in a 1-to-1 ratio, this had to be a 2 plus. So this would actually be copper 2 carbonate, okay? That would be the answer here. So I'm going to put copper, and then Roman numerals 2, and then carbonate. Okay? All right, and then part B. This is one of the few cations that you have to know, one of the 2 cations that you have to know for this test. You should just recognize it just as is. This is called ammonium. So I'm going to just write ammonium. Think of Ammon, like from the Book of Mormon, and then just add an inium. So ammonium. All right, so we got ammonium, and then it's combined with, what is this? That's PO4, and I know that it had some sort of charge. Let's look at the PO4. PO4 was down here, and we said that was phosphate. Okay, so phosphate. We got ammonium, phosphate. And actually, that's it. That's all you have to do. We don't have to put Roman numerals, because Roman numerals will only be done with transition metals, meaning the ones that are down here. I'm just going to put Roman numerals down here. Okay, Roman numerals. Those are the only places. Why? Because these ions, these metals, can take on ions that are of different values. So like iron has a 1 plus or a 2 plus, or it can have even up to a 3 plus. Whereas these guys over here, these metals, are specific. This group 2 was always going to have a 2 plus, always. This group here is always going to have a 1 plus. Okay, but these metals in here don't, and so that's why we have to differentiate them when we're writing them out via Roman numerals, okay? So now we've got this guy. So remember, this is mercury. So I'm just going to write mercury. And then this is SO4. Now, they come together in a 1-to-1 ratio, right? And so I remember that sulfate had that 2 charge, and it's got the 4 oxygens, so that's going to be mercury sulfate. All right. Now, D, I've got this. What is this? That is, in the periodic table, that's magnesium. That's magnesium. So I'm going to write magnesium. All right. And then what is the next? What is this polyatomic ion? This is an O3. And remember, anything that has O3 other than sulfate and phosphate are just going to be the 8 base ions. Okay, so this is going to be nitrate. And that's it. That's all you have to say, magnesium nitrate, because we don't have to designate any Roman numerals for these. All right, so now look at this. We actually have an acid here. This H, if the compound is not charged, which it's not, then you're going to assume that this is an acid, and so you have to follow acid naming rules. So what you have to look at first is this part, the part that the H is attached to. So hopefully you recognize it. This was one that we did earlier. This was hypochlorite. Okay, now remember the adic to itis. That was our rule for naming acids. Okay, so I noticed that this is called hypochlorite. Ends in ite. Okay, so to make this an acid, all I'd have to do is change the ite to an us and then say acid. So hypochlorous acid. That's it. Hypochlorous acid. And the reason I knew I had to name it after an acid was because this was not charged. Okay. Sometimes we see hydrogen attached, but the substance is still charged, like bicarbonate, right? That has a different name. It can actually act as an acid, but we don't refer to it as an acid in the name. Okay. So, but when we have it alone like this and it's a neutral compound, then we do. Okay. Hopefully that made sense. All right. So barium is in the second group of the periodic table, so it's got a 2+ charge. I'm going to put 2+. And then what is this? This is okay, so there's one hydrogen and then a sulfate, right? O4. So let's write out what this originally was. This was Ba2+, and then this was HSO4-. Can you see how we got the chemical formula from that? Right? We switched this 2 over here and then the 1 over there. So what would we call this? We would just say this is barium. Okay, barium, and then we just say bisulfate. Okay, that's it. All right, last one. We've got this metal right here. What is that? That is lithium, and lithium is in the first row or first group of the periodic table. So it has a 1+, and we've got this ion here. Okay, what was this? ClO4. That was when we had to add the per, right? The per 8. So now this is going to be lithium, and then this is perchlorate. Right, this was a chlorine, so I had to add the per and the 8, and then this was chlorine, so I added the chlor to make it lithium perchlorate. Okay, all right. I hope that kind of made it a little simpler for naming. If you can follow these patterns, again, you're welcome to have screenshotted this or taken a picture. This pattern, as long as you can understand it, and then know at least some of the exceptions to it as well. I feel like it'll make memorizing these names a lot easier and naming ionic compounds a lot easier as well. Okay. All right, number 7, potassium nitrate has many uses. And honestly, just ignore the rest of this. This is all just, fun fact stuff. It doesn't really help us with the problem. So I'm going to skip down to the question. It says, how many grams of nitrogen are found in 100 grams of potassium nitrate? So let's figure out what potassium nitrate looks like first. So first we got the potassium ion, which is K+, right? We know that it's in the first group of the periodic table. From up here when we were doing this earlier. And now we got nitrate. Okay, what was nitrate? 8s. Remember, 8s are usually O3- with the exception of sulfate and phosphate, which are O4-, right? So now when I switch these superscripts, I get a 1-to-1 ratio and I get KNO3. That's it. So now what we're trying to figure out is how many grams of nitrogen are found in 100 grams of this substance right here, potassium nitrate. So I'm going to say 100 grams of KNO3. Now, the one thing that you need to know or figure out how to do is just know the molar mass for this, and we've covered this before, so hopefully you know how to do this. I've previously looked it up here, and it's about 101.1 grams per 1 mole, okay, of KNO3. Now, for every 1 mole of KNO3, we're looking for how many, we can technically turn this into moles of nitrogen, right? So for every 1 mole of KNO3, I also have 1 mole of K, I have 1 mole of N, I have 3 moles of oxygen, okay? So for every 1 mole of this you'll have 1 of each of these and then 3 of oxygen, okay? So that means for every 1 mole of KNO3 here in the dimensional analysis, I can actually put 1 mole of nitrogen, okay? So for every 1 mole of that substance I know that I have that many moles of nitrogen. And then using the molar or the atomic weight of nitrogen, we can just say I know that in 1 mole of nitrogen, if you look on the periodic table, its molar or atomic mass is 14.007 grams for nitrogen. Okay, and then I can cancel this, cancel that, cancel this, cancel that, cancel this, and then cancel that. And ultimately, you should get an answer that's in grams of nitrogen, okay? And ultimately, that ends up being about 13.85 grams of nitrogen, okay, in this 100 grams of potassium nitrate. You could argue some sig figs here. This could ultimately be 13.9 if we had a decimal here. They didn't ask us for sig figs, so I'm just going to place this as is. When you have a free response on the test, though, maybe it might be, especially if they ask for it, I would put it in there just in case, okay? Number 8. Okay, the compound COCl2 has been used as a chemical warfare agent, and it too, okay, blah, blah, blah. Now, they're talking about these two substances and this substance. Okay, now rank the compounds in order of decreasing polarity between the carbon and the halogen. Okay, remember the halogen is either chlorine, iodine, or bromine. Those are the ones that are in the halogens family on the periodic table. So you don't have to know what this compound looks like, but you know that the carbon and the chlorine and the carbon and the bromine and the carbon and the iodine are all attached to each other, right? Now let's determine which one is the most polar. Remember, polarity in terms of the trends on the periodic table has to do with the electronegativity, right? So the further up and to the right you are, the more electronegative you are, more electronegative, okay? Meaning, since they're all bound to carbon, the only thing that differentiates them is what their actual electronegativity value is. So if I just look here, I see that chlorine's is a lot bigger, and so that the difference between chlorine and carbon is going to be bigger, meaning the polarity is going to be stronger. Does that make sense? So that because the difference in electronegativity here is bigger between chlorine and carbon, it's going to be a bigger difference than the difference between bromine and carbon, or than iodine and carbon, because we follow this trend upward and to the right with electronegativity. So in terms of increasing strength, we would say COCl2 is greater than COBr2, which is greater than COI2, but they asked us in terms of decreasing, so I'm going to say, I'm just going to put the less than sign here. Boom. Okay. And so that's how we would look at polarity. Remember, we look at the electronegativity values for those on the periodic table. All right, that'll finish it for problem set 10. I hope this was helpful. We'll see you in the next video.